Internet Relay Chat.
Internet Relay Chat is a system that facilitates transfer of messages in the form of text. The chat process works on a client-server model of networking. IRC clients are computer programs that a user can install on their system. These clients are able to communicate with chat servers to transfer messages to other clients. It is mainly designed for group communication in discussion forums, called channels, but also allows one-to-one communication via private message as well as chat and data transfer, including file sharing. Client software is available for every major operating system that supports Internet access. As of April 2011, the top 100 IRC networks served more than 500,000 users at a time, with hundreds of thousands of channels operating on a total of roughly 1,500 servers out of roughly 3,200 servers worldwide.
History.
IRC was created by Jarkko Oikarinen in August 1988 to replace a program called MUT, Multi-User Talk, on a BBS called Box in Finland. Oikarinen found inspiration in a chat system known as Bitnet Relay, which operated on the BITNET. IRC was used to report on the 1991 Soviet coup d'état attempt throughout a media blackout. It was previously used in a similar fashion during the Gulf War. Logs of these and other events are kept in the iBiblio-archive.
Technical information.
IRC is an open protocol that uses TCP and, optionally, TLS. An IRC server can connect to other IRC servers to expand the IRC network. Users access IRC networks by connecting a client to a server. There are many client implementations, such as MISC, XCHAT and IRC, and server implementations, for example the original IRCD. Most IRC servers do not require users to register an account, but a user will have to set a nickname before being connected. IRC was originally a plain text protocol, although later extended, which on request was assigned port 194/TCP by IANA. However, the de facto standard has always been to run IRC on 6667/TCP in nearby port numbers, for example TCP ports 6660 to 6669, 7000, to avoid having to run the IRCD software with root privileges. The protocol specified that characters were 8-bit but did not specify the character encoding the text was supposed to use. This can cause problems when users using different clients and/or different platforms want to converse. All client-to-server IRC protocols in use today are descended from the protocol implemented in the IRC 2.4.0 version of the IRC2 server, and documented in RFC 1459. Since RFC 1459 was published, the new features in the IRC 2.10 implementation led to the publication of several revised protocol documents, RFC 2810, RFC 2811, RFC 2812 and RFC 2813. However, these protocol changes have not been widely adopted among other implementations. Although many specifications on the IRC protocol have been published, there is no official specification, as the protocol remains dynamic. Virtually no clients and very few servers rely strictly on the above RFCs as a reference. Microsoft made an extension for IRC in 1998 via the proprietary IRCX. They later stopped distributing software supporting IRCX, instead developing the proprietary MSMP. The standard structure of a network of IRC servers is a tree. Messages are routed along only necessary branches of the tree, but network state is sent to every server and there is generally a high degree of implicit trust between servers. This architecture has a number of problems. A misbehaving or malicious server can cause major damage to the network, and any changes in structure, whether intentional or a result of conditions on the underlying network, require a net split and net join. This results in a lot of network traffic and spurious quit join messages to users and temporary loss of communication to users on the splitting servers. Adding a server to a large network means a large background bandwidth load on the network and a large memory load on the server. Once established, however, each message to multiple recipients is delivered in a fashion similar to multicast, meaning each message travels a network link exactly once. This is a strength in comparison to non-multicasting protocols such as Simple Mail Transfer Protocol, SMTP, or Extensible Messaging and Presence Protocol, XMPP.
Commands and replies.
IRC has a line-based structure with the client sending single-line messages to the server, receiving replies to those messages and receiving copies of some messages sent by other clients. In most clients, users can enter commands by prefixing them with a slash. Depending on the command, these may either be handled entirely by the client, or, generally for commands the client does not recognize, pass directly to the server, possibly with some modification. Due to the nature of the protocol, automated systems cannot always correctly pair a sent command with its reply with full reliability and are subject to guessing.
Channels.
The basic means of communicating to a group of users in an established IRC session is through a channel. Channels on a network can be displayed using the IRC command list, which lists all currently available channels that do not have the modes +S or +P set on that particular network. Users can join a channel using the join command, in most clients available as /join channel name. Messages sent to the join channels are then relayed to all other users. Channels that are available across an entire IRC network are prefixed with a pound, while those local to a server use ampersand. Other less common channel types include plus channels, modeless channels without operators, and exclamation mark channels, a form of timestamp channel on normally non-timestamped networks.
Modes.
Users and channels may have modes that are represented by single case-sensitive letters and are set using the mode command. User modes and channel modes are separate and can use the same letter to mean different things. For example, user mode I is invisible mode whilst channel mode I is invite only. Modes are usually set and unset using the mode command that takes a target, user or channel, a set of modes to set, plus or unset, and any parameters the modes need. Some but not all channel modes take parameters and some channel modes apply to a user on a channel or add or remove a mask, for example a ban mask, from a list associated with the channel rather than applying to the channel as a whole. Modes that apply to users on a channel have an associated symbol that is used to represent the mode in names replies, sent to clients on first joining a channel and use of the names command, and in many clients also used to represent it in the client's displayed list of users in a channel or to display a known indicator for a user's modes. In order to correctly parse incoming mode messages and track channel state, the client must know which mode is of which type and for the modes that apply to a user on a channel which symbol goes with which letter. In early implementations of IRC this had to be hard-coded in the client, but there is now a de facto standard extension to the protocol called iSupport that sends this information to the client at connect time using numeric 005. There is a small design fault in IRC regarding modes that apply to users on channels. The names message used to establish initial channel state can only send one such mode per user on the channel, but multiple such modes can be set on a single user. For example, if a user holds both operator status, +O, and voice status, +V, on a channel, a new client will be unable to know the less precedented mode, voice. Workarounds for this are possible on both the client and server side, but none is widely implemented.
Standard RFC 1459, modes.
Many IRCD programmers have added extra modes or modified the behavior of modes in the above list, so it is strongly advisable to check the documentation of the IRC network or IRCD, though note that the network may have patched the IRCD, for more detailed information on what the modes do on a particular server or network.
Channel operators.
A channel operator is a client on an IRC channel that manages the channel. IRC channel operators can be easily seen by a symbol at, or a Latin letter +O/O. On most networks, an operator can kick a user, ban a user, Give other user IRC channel operator status or IRC channel voice status. Change the IRC channel topic. Change the IRC channel mode locks.
IRC operators.
There are also users who maintain elevated rights on their local server, or the entire network. These are called IRC operators, sometimes shortened to IRCops or OPers, not to be confused with channel operators. As the implementation of the IRCD varies, so do the privileges of the IRC operator on the given IRCD. RFC 1459 claims that IRC operators are a necessary evil to keep clean state of the network, and as such they need to be able to disconnect and reconnect servers. Additionally, to prevent malicious users or even harmful automated programs from entering IRC operators are usually allowed to disconnect clients and completely ban IPs or complete subnets. Networks that carry services, NICs of AL, usually allow their IRC operators also to handle basic ownership matters. Further privileged rights may include overriding channel bans, being able to join channels they would not be allowed to join, if they were not OPed, being able to opt themselves on channels where they would not be able without being OPed, being auto-opt on channels always and so forth.
Host masks.
A host mask is a unique identifier of an IRC client connected to an IRC server. IRC servers, services, and other clients including bots can use it to identify a specific IRC session. The format of a host mask is NIC. User at host. The host mask looks similar to, but should not be confused with an email address. The NIC part is the nickname chosen by the user and may be changed while connected. The user part is the username reported by ident on the client. If ident is not available on the client, the username specified when the client connected is used after being prefixed with a tilde. The host part is the host name the client is connecting from. If the IP address of the client cannot be resolved to a valid host name by the server, it is used instead of the host name. Because of the privacy implications of exposing the IP address or host name of a client, some IRC daemons also provide privacy features, such as INSP IRCD or Unreal IRCDs plus X mode. This hashes a client IP address or masks part of a client's host name, making it unreadable to users other than IRCops. Users may also have the option of requesting a virtual host, or VHOST, to be displayed in the host mask to allow further anonymity. Some IRC networks such as Freenode use these as cloaks to indicate that a user is affiliated with a group or project.
Challenges.
Issues in the original design of IRC were the amount of shared state data being a limitation on its scalability, the absence of unique user identifications leading to the nickname collision problem, lack of protection from NIT splits by means of cyclic routing, the trade-off in scalability for the sake of real-time user presence information, protocol weaknesses providing a platform for abuse, no transparent and optimizable message passing, and no encryption. Some of these issues have been addressed in modern IRC.
Attacks.
Because IRC connections are usually unencrypted and typically span long time periods, they are an attractive target for DOS/DDoS attackers and hackers. Because of this, careful security policy is necessary to ensure that an IRC network is not susceptible to an attack such as a takeover war. IRC networks may also K-line or G-line users or networks that have a harming effect. A small number of IRC servers support SSL/TLS connections for security purposes. This helps stop the use of packet sniffer programs to obtain the passwords of IRC users, but has little use beyond this scope due to the public nature of IRC channels. SSL connections require both client and server support, that may require the user to install SSL binaries and IRC client-specific patches or modules on their computers. Some networks also use SSL for server-to-server connections, and provide a special channel flag, such as +S, to only allow SSL-connected users on the channel, while disallowing operator identification in clear text, to better utilize the advantages that SSL provides. IRC served as an early laboratory for many kinds of Internet attacks, such as using fake ICMP unreachable messages to break TCP-based IRC connections, nuking, to annoy users or facilitate takeovers.
Abuse prevention.
One of the most contentious technical issues surrounding IRC implementations, which survives to this day, is the merit of NIC channel delay versus timestamp protocols. Both methods exist to solve the problem of denial of service attacks, but take very different approaches. The problem with the original IRC protocol as implemented was that when two servers split and rejoined, the two sides of the network would simply merge their channels. If a user could join on a split server, where a channel that existed on the other side of the network was empty, and gain operator status, they would become a channel operator of the combined channel after the NIT split ended. If a user took a nickname that existed on the other side of the network, the server would kill both users when rejoining, that is, NIC collision. This was often abused to mass kill all users on a channel, thus creating opless channels where no operators were present to deal with abuse. Apart from causing problems within IRC, this encouraged people to conduct denial of service attacks against IRC servers in order to cause NIT splits, which they would then abuse.
NIC channel delay.
The NIC channel delay, abbreviated NDCD, solution to this problem was very simple. After a user signed off and the nickname became available, or a channel ceased to exist because all its users left, as often happens during a NIT split, the server would not allow any user to use that nickname or join the channel, until a certain period of time, the delay, had passed. The idea behind this was that even if a NIT split occurred, it was useless to an abuser because they could not take the nickname or gain operator status on a channel, and thus no collision of a nickname or merging of a channel could occur. To some extent, this inconvenienced legitimate users, who might be forced to briefly use a different name. Appending an underscore was popular, after rejoining.
Timestamping.
The alternative, the timestamp or TS protocol, took a different approach. Every nickname and channel on the network was assigned a timestamp, the date and time when it was created. When a NIT split occurred, two users on each side were free to use the same nickname or channel, but when the two sides were joined, only one could survive. In the case of nicknames, the newer user, according to their TS, was killed. When a channel collided, the members, users on the channel, were merged, but the channel operators on the losing side of the split lost their channel operator status. TS is a much more complicated protocol than NDCD, both in design and implementation, and despite having gone through several revisions, some implementations still have problems with desyncs, where two servers on the same network disagree about the current state of the network, and allowing too much leniency in what was allowed by the losing side. Under the original TS protocols, for example, there was no protection against users setting bands or other modes in the losing channel that would then be merged when the split rejoined, even though the users who had set those modes lost their channel operator status. Some modern TS-based IRC servers have also incorporated some form of ND and/or CD in addition to timestamping in an attempt to further curb abuse. Most networks today use the timestamping approach. The timestamp versus NDCD disagreements caused several servers to split away from Ethernet and form the newer ERCnet. After the split, Ethernet moved to a TS protocol, while ERCnet used NDCD.
Save.
In recent versions of the ERCnet IRCD, as well as IRCDS using the TS6 protocol, including Charybdis and INSP IRCD, AND-D has been extended replaced by a mechanism called save. This mechanism assigns every client a unique UID upon connecting to an IRC server. This ID starts with a number, which is forbidden in NICs, although some IRCDS, namely ERCnet and INSP IRCD, allow clients to switch to their own UID as the nickname. If two clients with the same nickname join from different sides of a NIT split, NIC collision, the first server to see this collision will force both clients to change their NIC to their UID, thus saving both clients from being disconnected. On ERCnet, The nickname will also be locked for some time, ND, to prevent both clients from changing back to the original nickname, thus colliding again.
Networks.
There are thousands of running IRC networks in the world. They run various implementations of IRC servers, and are administered by various groups of IRC operators, but the protocol exposed to IRC users is very similar, and all IRC networks can be accessed by the same client software, although there might be slight incompatibilities and limited functionality due to the differing server implementations. The largest IRC networks have traditionally been grouped as the Big Four, a designation for networks that top the statistics. The Big Four networks change periodically, but due to the community nature of IRC there are a large number of other networks for users to choose from. Historically the Big Four were Ethernet, ERCnet, Undernet, Dalnet. IRC reached 6 million simultaneous users in 2001 and 10 million users in 2003. As of March 2013 the largest IRC networks were Freenode, around 85k users at peak hours, ERCnet, around 55k users at peak hours, QuakeNet, around 53k users at peak hours, Undernet, around 43k users at peak hours, Ethernet, around 33k users at peak hours, Risen, around 20k users at peak hours. Today, entire IRC grouped has around 400k users at peak hours.
Timeline. URI scheme.
There are 3 recognized URI schemes for Internet Relay Chat, ERC, ERC6, and ERCs, that, when supported, allows hyperlinks of various forms, including where items enclosed within brackets are optional, to be used to, if necessary, connect to the specified host, or network, if known to the IRC client, and join the specified channel. This can be used within the client itself, or from another application such as a web browser. ERC is the default URI. ERC6 specifies a connection to be made using IPv6, and ERC specifies a secure connection. Per the specification, the usual hash symbol will be prepended to channel names that do not begin with an alphanumeric character, allowing it to be omitted. Some implementations, for example, MISE, will do so unconditionally, resulting in a, usually unintended, extra, for example, channel, if included in the URL. Some implementations allow multiple channels to be specified, separated by commas.
Clients. Client software.
Client software exists for various operating systems or software packages, as well as web-based or inside games. Many different clients are available for the various operating systems, including Windows, Unix and Linux, Mac OS X and mobile operating systems, such as iOS and Android. On Windows, MISE is one of the most popular clients. The higher-level programs also serve as platforms for the IRC clients. For instance, a client called ERC, written entirely in Emacs Lisp, is included in v22.3 of Emacs. Therefore, any platform that can run Emacs can run ERC. A number of web browsers have built-in IRC clients, such as Opera or the Chatzilla add-on for Mozilla Firefox, included as a built-in component of SeaMonkey. Web-based clients, such as Mibit, can run in most browsers. Games such as Pokémon Amiga Warsaw, Unreal Tournament, up to Unreal Tournament 2004, Upperlink, Spring Engine-based games, Zero AD and Zdaemon have included IRC. Ustream's chat interface is IRC with custom authentication as well as just-in TVs.
Bots.
Bot is derived from the word robot, and is an automated process that interacts with other network services. Bots often automate tasks and provide information or services that would otherwise be conducted by a human being. A typical use of bots is to gather information, such as web crawlers, or interact automatically with instant messaging, IM, Internet Relay Chat, IRC, or other web interfaces. They may also be used to interact dynamically with websites. Bots can be used for either good or malicious intent. A malicious bot is self-propagating malware designed to infect a host and connect back to a central server or servers that act as a command and control (CNC) center for an entire network of compromised devices, or botnet. With a botnet, attackers can launch broad-based, remote control, flood-type attacks against their target. In addition to the worm-like ability to self-propagate, bots can include the ability to log keystrokes, gather passwords, capture and analyze packets, gather financial information, launch DOS attacks, relay spam, and open backdoors on the infected host. Bots have all the advantages of worms, but are generally much more versatile in their infection vector, and are often modified within hours of publication of a new exploit. They have been known to exploit backdoors opened by worms and viruses, which allows them to access networks that have good perimeter control. Bots rarely announce their presence with high scan rates, which damage network infrastructure. Instead, they infect networks in a way that escapes immediate notice.
Exploit.
An exploit is a piece of software, a command, or a methodology that attacks a particular security vulnerability. Exploits are not always malicious in intent, they are sometimes used only as a way of demonstrating that a vulnerability exists. However, they are a common component of malware.
Backdoor.
A backdoor is an undocumented way of accessing a system, bypassing the normal authentication mechanisms. Some backdoors are placed in the software by the original programmer and others are placed on systems through a system compromise, such as a virus or worm. Usually, attackers use backdoors for easier and continued access to a system after it has been compromised.
Bouncer.
A program that runs as a daemon on a server and functions as a persistent proxy is known as a BNC or bouncer. The purpose is to maintain a connection to an IRC server, acting as a relay between the server and client, or simply to act as a proxy. Should the client lose network connectivity, the BNC may stay connected and archive all traffic for later delivery, allowing the user to resume his IRC session without disrupting their connection to the server. Furthermore, as a way of obtaining a bouncer-like effect, an IRC client, typically text-based, for example IRC, may be run on an always-on server to which the user connects via SSH. This also allows devices that only have SSH functionality, but no actual IRC client installed themselves, to connect to the IRC, and it allows sharing of IRC sessions. To keep the IRC client from quitting when the SSH connection closes, the client can be run inside a piece of screen detaching software, for example GNU Screen OTMU, thus staying connected to the IRC network, constantly and able to log conversation in channels that the user is interested in, etc. Modeled after this setup, in 2004 an IRC client following the client-server model, called SMUI, has been launched.
Search engines.
There are numerous search engines available to aid the user in finding what they are looking for on IRC. Generally the search engine consists of two parts, a back-end, or spider crawler, and a front-end search engine. The back-end, spider crawler, is the workhorse of the search engine. It is responsible for crawling IRC servers to index the information being sent across them. The information that is indexed usually consists solely of channel text, text that is publicly displayed in public channels. The storage method is usually some sort of relational database, like MySQL or Oracle. The front-end search engine is the user interface to the database. It supplies users with a way to search the database of indexed information to retrieve the data they are looking for. These front-end search engines can also be coded in numerous programming languages. The more popular languages for such search engines and indexing spiders are Perl, PHP and C. Most search engines have their own spider that is a single application responsible for crawling IRC and indexing data itself. However, others are user-based indexers. The latter rely on users to install their add-on to their IRC client. The add-on is what sends the database the channel information of whatever channels the user happens to be on.
Modern IRC.
IRC has changed much over its life on the Internet. New server software has added a multitude of new features. Services, network-operated bots to facilitate registration of nicknames and channels, sending messages for offline users and network operator functions, extra modes. While the original IRC system used a set of standard user and channel modes, new servers add many new modes for such features as removing color codes from text, or obscuring a user's hostmask, cloaking to protect from denial of service attacks, proxy detection. Most modern servers support detection of users attempting to connect through an insecure, misconfigured or exploited, proxy server, which can then be denied a connection. An example is the Blitzed Open Proxy Monitor or BOPM. This proxy detection software is used by several networks, although that real-time list of proxies is defunct since early 2006. Additional commands. New commands can be such things as shorthand commands to issue commands to services, to network operator-only commands to manipulate a user's hostmask. Encryption. For the client-to-server leg of the connection SSL might be used. Messages cease to be secure once they are relayed to other users on standard connections, but it makes eavesdropping on or wiretapping an individual's IRC sessions difficult. For client-to-client communication, SDCC, Secure DCC, can be used. Connection protocol, IRC can be connected to via IPv4, the current standard version of the Internet Protocol, or by IPv6, the next-generation version of the protocol. There is an effort of standardization and adding new features to the IRC protocol by a CV3 working group.
Character encoding.
IRC still lacks a single globally accepted standard convention for how to transmit characters outside the 7-bit ASCII repertoire. IRC servers normally transfer messages from a client to another client just as byte sequences, without any interpretation or recoding of characters. The IRC protocol, unlike for example MIME or HTTP, lacks mechanisms for announcing and negotiation character encoding options. This has put the responsibility for choosing the appropriate character codec on the client. In practice, IRC channels have largely used the same character encodings that were also used by operating systems, in particular Unix derivatives, in the respective language communities. 7-bit era. In the early days of IRC, especially among Scandinavian and Finnish language users, national variants of ISO 646 were the dominant character encodings. These encode non-ASCII characters like AOA at code position 0x5b 0x5c 0x5d 0x7b 0x7c 0x7d, us ASCII. That is why these codes are always allowed in nicknames. According to RFC 1459, in nicknames should be treated as lowercase equivalents of respectively. By the late 1990s, the use of 7-bit encodings had disappeared in favor of ISO 8859-1, and such equivalence mappings were dropped from some IRC daemons. 8-bit era. Since the early 1990s, 8-bit encodings such as ISO 8859-1 have become commonly used for European languages. Russian users had a choice of KOI8R, ISO 8859-5 and CP1251, and since about 2000, modern Russian IRC networks convert between these different commonly used encodings of the Cyrillic script. Multi-byte era. For a long time, East Asian IRC channels with ideographic scripts in China, Japan, and Korea have been using multi-byte encodings such as EUC or ISO 2022 JP. With the common migration from ISO 8859 to UTF-8 on Linux and Unix platforms since about 2002, UTF-8 has become an increasingly popular substitute for many of the previously used 8-bit encodings in European channels. Some IRC clients are now capable of reading messages both in ISO 8859-1 or UTF-8 in the same channel, heuristically auto-detecting which encoding is used. The shift to UTF-8 began in particular on Finnish-speaking IRC, Merkisto, Finnish. Today, The UTF-8 encoding of Unicode ISO 10646 would be the most likely contender for a single future standard character encoding for all IRC communication, if such standard ever relaxed the 510 bytes message size restriction. UTF-8 is ASCII compatible and covers the superset of all other commonly used coded character set standards.
File sharing.
Much like conventional P2P file sharing, users can create file servers that allow them to share files with each other by using customized IRC bots or scripts for their IRC client. Often users will group together to distribute a res via a network of IRC bots. Technically, IRC provides no file transfer mechanisms itself. File sharing is implemented by IRC clients, typically using the Direct Client-to-Client (DCC) protocol, in which file transfers are negotiated through the exchange of private messages between clients. The vast majority of IRC clients feature support for DCC file transfers, hence the view that file sharing is an integral feature of IRC. The commonplace usage of this protocol, however, sometimes also causes DCC spam. DCC commands have also been used to exploit vulnerable clients into performing an action such as disconnecting from the server or exiting the client.